Why does a straw appear bent when placed in a glass of water? Why can radio signals sometimes travel beyond the horizon? And why do satellite and radar engineers care about atmospheric conditions? The answer lies in a phenomenon called refraction, where electromagnetic waves change direction as they move between different materials. In the previous lesson, we learned that when an electromagnetic wave encounters a boundary, part of its energy may be reflected. However, reflection is not the only possible outcome. In many situations, a significant portion of the wave continues into the second medium instead of bouncing back. An interesting observation occurs when the wave enters the new material at an angle. Rather than continuing in a straight line, the wave changes direction. This bending behavior can be observed in light, radio waves, radar signals, and many other electromagnetic systems. The challenge is understanding why this change in direction occurs. What causes a wave to bend simply because it enters a different material? To answer this question, we need to understand refraction. Refraction is the change in direction of an electromagnetic wave as it passes from one medium into another medium with different propagation properties. The fundamental cause of refraction is a change in wave velocity. As we learned earlier, electromagnetic waves travel at different speeds in different materials. When a wave crosses a boundary and its speed changes, its direction often changes as well. The amount of bending depends on the properties of the two media and the angle at which the wave arrives. If the speed difference between the materials is large, the change in direction can be significant. If the materials have similar properties, only a small amount of bending occurs. Intuitively, imagine a marching band moving diagonally from a paved road into soft sand. The musicians who enter the sand first slow down before the others. As a result, the entire formation changes direction. Electromagnetic waves behave in a very similar way when entering a medium where propagation speed changes. Physically, consider a beam of light traveling from air into water. Because light travels more slowly in water, the wavefront changes direction as it enters the new medium. This bending creates familiar optical effects, such as objects appearing displaced beneath the water surface. Mathematically, refraction is described by Snell's law, which relates the angles and propagation speeds in the two media. The law allows engineers to predict exactly how much a wave will bend when crossing a material boundary. Refraction plays an important role in RF engineering because radio waves frequently travel through media with varying electromagnetic properties. The atmosphere itself is not perfectly uniform, and changes in temperature, pressure, and humidity can influence propagation. In long-range communication systems, atmospheric refraction can cause radio signals to bend slightly toward the Earth, extending communication range beyond what would be expected from simple line-of-sight geometry. Similar effects influence radar performance and satellite communication links. At the system level, refraction affects microwave links, radar systems, satellite communications, wireless propagation modeling, and remote sensing applications. Engineers must account for these effects when designing high-performance communication systems. Refraction demonstrates that electromagnetic waves are strongly influenced by the properties of the environment through which they travel. Even when no reflection occurs, a wave may still experience significant changes in direction and behavior. A common misconception is that refraction only applies to visible light. In reality, all electromagnetic waves, including radio waves, microwaves, infrared radiation, and radar signals can undergo refraction when moving between media with different electromagnetic characteristics. When reflected waves and incident waves exist simultaneously, another interesting phenomenon can occur. Instead of simply traveling away, the waves can combine to form stationary patterns. In the next lesson, we will explore standing waves and discover why they are critically important in RF systems and transmission lines. In this lesson, we learned that refraction occurs when an electromagnetic wave changes direction as it moves between materials with different propagation speeds. We also saw how refraction affects light, radio waves, radar systems, and long-distance communication links. In the next lesson, We will explore standing waves and discover how interacting waves can create stationary patterns that influence power transfer and RF system performance. If you found this useful, like the video, subscribe, and follow for the next lesson.